Okay, so good morning and happy Friday to everyone. Today we're going to study determinants and two byproducts to immediate applications. So we're going to see the properties of determinants. And we're going to look at the explicit formula for the inverse of a matrix. Yeah, we can do that using determinants. It's quite interesting. And of course, last but not least, we're going to see Cramer's rule. So there are different ways to introduce determinants, but for all intents and purposes, the determinant of a square matrix is a number assigned to it in a very specific way. And we're going to describe this way, or one of those possible ways, right away. So first of all, let me just say that so far we have been denoting matrices in two ways. So, it's, and you should feel perfectly fine. In literature, I think there is, I want to say one more way with something that looks like double brackets. But so far, our notation for a matrix has been like this, and I have not expressed any particular preference. It seems to me that I'm using the parentheses more than the bracket, but so far these have been our two possible notations for matrices in this course. Our two possible notations, and they're the most standard ones in mathematical literature. I don't even know if one is more frequent than the other. I think both of them are used really frequently. Are two possible notations for a matrix. But we will have, we will denote a determinant by simply replacing either the parentheses or the brackets, depending on what you prefer, by vertical lines. So here you have to be careful. I mean, the determinant should not be denoted any other way. Okay, so that's the notation for determinant. And the possible alternative that we will have sometimes is that determinant of A, so like this, will also denote the determinant of the matrix A. So this, you do this in more theoretical cases. So when you don't know what the matrix is, and you just want to reference directly its determinant, we're going to be doing it this way. Again, here you can find in the literature the vertical lines over A. I'm not going to use this notation. I will use this notation if I have to talk about the determinant of an abstract matrix. Okay. So what is the determinant that you all know? And what we're going to do today is going to be a great generalization. You've all seen this determinant, the 2x2 determinant, right? And I think the work in Calc 3 suggests that you have seen also the 3x3 determinant. I will remind you how we were computing it in Calc 3, because this will be intimately connected with the first general definition of the determinant that we're going to give here. So we were expanding with respect to the first row. So we delete the row in the column that contained the first entry, and that gives us the determinant B2, B3, C2, C3, which is a 2x2 determinant that can be computed, as we said before. Then we put minus A2. Determinants are highly alternating objects. You play with pluses and minuses as much as you can. So you delete the row in the column that contain A2, and what do you get? B1, B3, C1, C3. I remind you that this is how we were computing the cross product. And finally, mine plus A3 times the determinant that you get by deleting the row in the column that contain A3. So that would be B1, B2, C1, C2. Questions? So this is what everybody should know so far. There's this absurd thing that if you talk in terms of determinants, the determinant of a 1x1 matrix is the single entry itself. So you would write it like this, which of course seems a little strange to you because it has the same notation with the absolute value. Well, the good news is that in this course, we're never going to worry about 1x1 determinant. So, you know, we can leave this completely out of our considerations. Are there any questions so far? So allow me to use this as my starting point in order to give you the general definition of determinants. In other words, you can proceed exactly the same way. That is, the determinant can be, once you know how to compute a 3x3 determinant, then how do you do the 4x4? So for the 4x4, you will be doing exactly the same thing. So this will be A1 times the determinant that you get by deleting the row in the column that contain A1. So let me show it once so that you can see it. So what does it look like? So you delete the row and the column that contain A1, right? And you can see what determinant comes up. So what you get is B2, B3, B4, C2, C3, C4, D2, D3, D4. And then now you start doing the same thing with the other entries. The only thing you have to remember is that you alternate the sign. So it will be minus A2 times the determinant that you get by deleting the row in the column that contain, oh boy, these are the accidents that can happen sometimes. Sorry about this. So by deleting the row in the column that contain A2, and you can see which one it is. So this will be B1, B3. Ooh, what kind of B is this? That's a new letter, right? B3, B4, C1, C3, C4, D1, D3, D4, plus A3 times. Now you delete the third column, right? And what does that give you? That gives you B1, B2, B4, C1, C2, C4, D1, D2, D4, and eventually minus, and now you delete the last column. Right? like so. And you have minus A4 times B1, B2, B3, C1, C2, C3, D1, D2, D3. Okay, and that's your 4x4. If you want the 5x5, you play the exact same game.
Can I have two questions, sorry. First the question, how you complete the multiplication after that? Second question, that is, this is a matter
okay,
you begin.
Let's take one question at a time. Okay.
Okay.
So what do you mean by how do I compute the multiplication?
How you calculate for after that? So this is a multiplication. We should to say such as the previous one, AD minus BC. So for here, how I choose AD and where I have to begin and where I have to end. So it should to be AD minus BC.
My apologies. I still don't follow here. Because these are 3x3 determinants, and as I told you a moment ago, that's how you compute the 3x3 determinants. So you would have to compute the 3x3 determinants on the side by using this, and then you have 4 computations of that type afterwards. Okay, so in other words, the process by which a determinant is computed is inductive. Okay, meaning you express the 4x4 determinant in terms of 4 3x3 determinants, and then each of those 3x3 determinants is going to be computed in terms of 3 2x2 determinants. Okay.
Yeah, I understand that. Second, the question is, this is a matter where you begin or end. What I mean, that is, if you are in such as a minus B, a minus A2, so you should to begin from the column after that, or it's no.
Start from the beginning of the row, please. Start from the beginning of the row. Okay. But as I'm going to show you in a second, you can actually do this with respect to any row or column. Okay, so in other words, a determinant. So this is the expansion with respect to the first row. And you can always do that, but you can expand with respect to any other row. We may expand with respect to any other row or column. Okay, so we need to use the signs as follows. So do you see how in the previous example, the signs that I use somehow are plus for A1. So I'm not changing. If A1 was a negative number, it remains negative. If it was a positive, it remains positive. And then minus, plus, minus. You see how the signs alternate. So that's always how you should play this game. But when you start with the first row, you do plus, minus, plus, minus. And then if you continue with the second row, now you have to go minus, plus, minus, plus. And if you continue with the third row, plus, minus, plus, minus, and then minus, plus, minus, plus. And the same rows, the same signs apply if you use a column. So if you use a column, you have to use these signs. So let me give you an example. So for example, let's say that they tell you expand the 3x3 determinant, and why don't we do this computation now? 1, 2, 5, 3, 1, 6, 2, 1, 2, 3, 4. So let's say that somebody asks us to compute this determinant, and we decide to compute this determinant with respect to the second row, the second column. Okay, so what does that mean? That means that I'm going to take each entry from the second column. I'm going to put in front of it the corresponding sign. So the signs here, think about it this way. You can always find the signs by starting from the first entry of the first row and finding the entry of what you want, meaning the first entry of the first row is always a plus. So now the second entry of the first row, meaning the number 2, will come with a minus. And then if you move down that column, it should be minus, plus, minus. So why don't you give it a try and try to compute the determinant with respect to the second column, as I suggested, and then we'll do it together and see how this is done in this concrete case. Okay, let's see together now how it's going to be. So it's going to be minus 2 times the determinant that you get by deleting the row in the column that contain 2. So that's 3, 6, 2, 4. And then plus 1 times the determinant that you get by deleting the row in the column that contain 1. So that's 1, 5, 2, 4. And then minus 3. And this will be times the determinant that you get by deleting the second column in the third row, which is 1, 5, 3, 6. I would like to finish this computation. Please tell me if you have a question before I proceed with this computation.
Is the third row should to be minus 3 or 5?
I'm sorry, what is 5? So I'm expanding with respect to the middle column. So the numbers
sorry for that. Yeah.
Are 2, 1, and 3. And so the first and the last number receive an extra negative sign, which means that if they were already negative, they would become positive. But now I chose all of them to be positive so that you can see how the signs work. And the middle one will be positive. So now I can do the computation. So how much is the first determinant? It's 3 5 times 4 is 12, minus 2 times 6, also 12, that's 0. Plus 1 times, and then you have 1 times 4 is 4, minus 10 is negative 6. Minus 3 times 1 times 6 is 6, minus 15 is negative 9. Okay, so this will give you minus 6 plus 27, which is 21. And that's it. Okay. Any questions?
Yeah, I did compute this with the wrong way. That's respecting to the first row, which give me 20, the same result, 21 too.
Yeah, but of course it should give you the same result. I mean, we said that you have the option to expand with respect to any row or any column. If we were to find different results, that would be a problem, right? So you will find the same result no matter with respect to what row or to what column you compute. Okay, it seems. I mean, it seems like a very strange fact that no matter how you compute it, you're going to get the same thing, but that's exactly how it works. Okay.
Thank you.
Yeah, I'm sorry. What? So you start with a negative because we said that you always choose your signs in an alternating way so that the first entry on the left, on the top left, is plus. So for the 3 by 3 determinant, is if you start with this with plus, then it's plus minus plus. Then again, since you alternate, is minus plus minus, and then again it's plus minus plus, right? So which signs should you choose for the second column? Here are the signs that you should choose for the second column. These are exactly the extra signs that I put. So remember, these are put as extra signs. Okay, there was one more question regarding the algebra. I'm not understanding which algebra because I computed these determinants. And then the other thing is just algebra of integer numbers. But from those determinants, right? So 3 times 4, we have the formula that we wrote a moment ago, A, B, C, D. That's AD minus BC, right? I mean, this formula is indeed our starting point. Everybody should know the 2 by 2 determinant. Okay. Again, depending on the level of exposure that you have on this 2 by 2 determinants, here's what I would do as a good exercise at home. So we computed this, and one of you said that they did the computation with respect to the first row, and of course they found the same answer, which is 21. If I were you, as a nice little exercise, I would compute this in all 6 possible ways. What are the 6 possible ways? With respect to the first row, with respect to the second row, with respect to the third row, with respect to the first column, with respect to the second column, with respect to the third column. All 6 times you should find 21, obviously. Okay, this would be a great little exercise so that you get comfortable with determinants. But here's the this method works fine up to the 3 by 3 determinant. The 4 by 4 is already a stretch. Okay, I mean, it's not the most economical way. And we're going to see today how we're going to compute determinants in a much better way. Just to give you an idea, let's say for the sake of the argument, we have a few computer scientists among us, right? So for the sake of the argument, let's say that we wrote a program. The program would need to use recursion, right? There are languages that allow recursion. And let's say that we wrote a program. And of course, it's computers, so we expect computers to surprise us with their speed. And let's say for the sake of the argument that we gave it a 50 by 50 determinant, right? 50 by 50. Or let's say 100 by 100. Okay, let's make it 100 by 100. That's 10,000 numbers, by the way. A 100 by 100 matrix has 10,000 numbers. But you would say, okay, big deal now for a computer, 10,000 numbers, what is 10,000 numbers? And the computer was supposed to compute them in the way that we just showed. A human would never attempt that, but then it's a computer, right? So you have a 100 by 100 matrix. You want to compute the determinant exactly the way that I showed you. So you start with 100 by 100, and that will reduce to 100 to 199 by 99, and each of the 99 by 99 will reduce to 99, 98 by 98, and so on and so forth. How long do you guess it would take the program to execute fully? For you know, and let's say for the sake of the argument, we're dealing with 1-digit numbers. So the entries of this 100 by 100 matrix will be two-digit numbers. How long do you think a very efficiently written program that however uses the pattern that I gave you would take to execute? Any guesses? And you have one of those computers that execute what is the you see now you're getting it's 100 factorial operations, right? It's 100 factorial. So what do you think? What do you think it would take? Yeah, you're absolutely right. It could be even more than that. You can do the exact computation and give like, so find 100 factorial and give each operation like 1 nanosecond or something, or less than 1 picosecond, right? You would still see that it's not even billions. It's much more than billion years. Okay, that with the fastest computer, this tells you right away that this method is not the best choice for larger determinants, because otherwise it seems that we cannot compute such determinants. And I claim that we can. I claim that we can write a program that can compute 100 by 100 determinant in less than a second or something. How in the world can this be done? Of course, you don't know it yet. You haven't, I don't think you have seen determinants like this, but having sat in this class so far, what do you think is going to be the answer to our computation of determinants? Would anybody like to take a wild guess? No, Cramer's rule is just a method that allows you to solve systems, as we're going to see. Block, no. The answer is going to be, what is the method that we have been using over and over? And I told you that this is the method that, exactly. Gauss elimination method. A Gauss elimination method. Believe it or not, that's the best method. There's no geometry, at least the way that no, you can't use angles. You can't start taking no columns or rows. Okay, columns or rows. Yeah. Okay. I mean, that's a cool question. I really love the question that you asked, but it's not possible. Okay, it doesn't work that way. And you intrigued me. I mean, I don't know if you get something which has any meaning actually. Now that you asked about it, I don't know. I don't know. Okay. Now let's look at the properties of determinants, and it's the properties of determinants that are going to give us everything that we need. So, okay, so let's start by some very interesting properties. So the determinant of a matrix is actually the determinant of the identity matrix is 1. The determinant of a diagonal matrix is the product of the diagonal entries. But you know what the great news are here? That the determinant of any triangular matrix, and now by triangular, I mean upper triangular or lower triangular, it's again the same thing. This is great news. So if somebody tells you, what is the determinant of this matrix? Oops, I said determinant and I'm writing, so what is this determinant? So I don't have to use a matrix. What is this determinant? The answer is 15. And what is this determinant? The answer is 60. And what is this determinant? the answer is 27. Okay, so diagonal and triangular matrices are the nicest but matrices for to have when using determinants. Then the determinant of the product of two matrices, be careful here, they have to be square matrices, both of them, otherwise this equation doesn't make any sense anyway, is the determinant of A times the determinant of B. Okay, so determinant is multiplicative, right? That's an excellent property. And actually, if you think about it, this has also another interesting, that the determinant of A is non-zero if and only if A is invertible. So only inverted. So finding the determinant gives you a very easy way of knowing whether your matrix is invertible or not. It doesn't allow you to find the matrix, the inverse matrix right away, but at least you can tell whether it's invertible or not. Now, the determinant of A is different from zero if and only if the rows are linearly independent. And the determinant of A is different from zero if and only if the columns are linearly independent. You will have a very nice analogy between rows and columns. And the reason for that is because the determinant of a matrix is equal to the determinant of its transpose. Okay, that's a very useful thing to remember. So if you have, let's say, 3, 1, 5, 2, negative 1, 7, 4, 1, 3, that's the same thing as the determinant of 3, 1, 5, 2, negative 1, 7, 4, 1, 3. Okay. Let's pause here. Okay, I gave you enough properties. Let's pause for a second. I have a few more to go. And the ones that I'm about to give you are exactly the ones that have to do with row operations. Questions, please. Yeah, so if you have a matrix and you a square matrix and you consider its transpose, what is the transpose of a matrix? It's the matrix that has the same, that has as rows the columns of the original matrix, or as columns the rows of the original matrix. Take a look at it. How this row became a column right here. This row became a column right here. That's what it means with a transpose symbol. Okay? Then the two matrices, a matrix and its transpose, have the same determinant. Okay? Any more questions, please? Okay, now, the determinant Exactly. Exactly. That's why I wrote it. Oh, you know what? Yeah, both ways. It goes both ways. So the determinant is non-zero if and only if the matrix is invertible. If it's invertible, it's non-zero. If it's non-zero, then the matrix is invertible. Okay. The determinant as a function of any single row or column is a linear function. Okay, so what do I mean by this? What do I mean by this? So imagine, let's say I'm taking the second column, right? So my first column, I consider it fixed. That's why I put specific numbers. They don't have to be specific numbers, but let's say for the sake of the argument. And then the middle column is the sum of two columns. A1 plus B1, A2 plus B2, A3 plus B3. Then this will be 315, A1, A2, A3, minus 254, plus 315, B1, B2, B3, negative 254. Okay, so you can always distribute the determinant with respect to any single row or column, any single one. Be careful. Don't try to do anything similar to what you do when you add matrices. And same thing if the row or the column is multiplied by a specific number. So let's say that you have 7A1, 7A2, 7A3, and then you have minus 254. This is going to be 7 times 315, A1, A2, A3, minus 254. So you can multiply, you can factor out a number if a whole row or column is multiplied by it. And conversely, if you multiply a determinant by a number, you can put that number inside the determinant in a row or column of your choice. So if I had the 7 here, then I could choose to put it in the second column, or the first column, or the third column, or the first row, or the second row, or the third row. It's up to me to choose. Okay. Any questions here, please? Here comes maybe the most beautiful one, right? If we swap two rows or two columns, any guesses? What do you think is the effect of that to a determinant? What happens if we swap two rows or two columns? What do you think is going to happen? No, it's not the same. Remember what we said, determinants are highly alternating objects. So the determinant is multiplied by negative 1. Is multiplied by negative 1. So the simplest example, of course, is if you have this, then that's the opposite of 4, 7, 3, 5. I swap the two rows, right? How about if we perform the first type of row operation? So if we add a multiple of one row, same for columns, then what? What do you think will happen here? No, let me say it. I don't guess this. Then this is amazing. the determinant doesn't change. The determinant doesn't change. The truth is that I gave you all these properties. There are about 10 properties, give or take, right? The truth is that you don't need all of these properties. If somebody asked me, what is the minimal amount of properties that we could have given here so that we would have been we could have defined the determinant fully. Okay, then the answer is this. Somebody had asked me, this is just for theoretical purpose that I'm saying. This property, and this property imply everything else. Believe it or not, these three properties can give us everything else. Okay, which means in some sense that if you have such a structure that satisfies these three properties, then it has to be the determinant. I'm saying this just for theoretical purposes. I did mean to give you all these properties this way, so that because we're going to use them in different cases. I would like to do an example of how you would do a standard computation. So I would like to do a 4x4. So let me do a 4x4, right? So let's say that I want to compute. So now I'm going to show you that here's what you're going to do. You're going to use the Gauss elimination method to make it triangular. Once you make it triangular, then you can take the product of the diagonal entries. But you have to be a little careful. So let's give ourselves a 4x4. Okay, so let's give this one. Okay, I want a pivotal. Now, I can get a pivotal in two ways. Either I can factor out a 2 from the first column, from the first row. If I factor out a 2, how do you factor out a 2 from the first? So you put a 2 outside, and then you need to divide the whole row by 2. So it will be 1, 3 halves. Don't write this, don't write this, don't write this, don't write this. Okay, don't write this. I don't want to introduce denominators so soon. Okay, but I could do it this way. I can factor out the 2. You can literally factor out the 2 and divide everything on a row or column of your choice by that number. You can always do that. But I don't want to do that. In fact, what I will choose to do, and please note here that I'm putting equality signs. When you compute determinants, you have to work with equalities. Otherwise, you will lose track of what you have. So note this. This is very different from when we were applying the Gauss elimination method to matrices. So again, I'm going to denote the operations that I'm doing. So here I have this very lovely one. I want to use this as my pivotal. So row 1, I swap it with row 2. So I put a negative sign in front, and I have 1, 4, 2, -3, 2, 3, 5, 1, 3, 1, -1, 1, -2, 1, 0, 2. So far, so good? Now, I'm going to eliminate the first, all the entries below 1, which is now my pivotal, right? How do I do this? Row operations. And remember, row operations in case of determinant don't change the value. So it's going to be -2 row 1 plus row 2, -3 row 1 plus row 3, and 2 row 1 plus row 4. Equality sign, let's not forget our equality, and we will have 1, 4 to -3. I shouldn't forget the negative sign that I was carrying with me. These are small mistakes that we need to avoid. 0. -2 times 4 is -8 plus 3, that's -5. -2 times 2 is -2. -2 times 2 is -4 plus 5 is 1. The negative, what negative? The negative came from the very first operation, right? This operation, we swap 2 rows. When you swap 2 rows, you gain a negative sign in front, right? And -2 times -3 is 6 plus 1 is 7. Then I'm doing the second one, which is 0. Negative, can I distinguish what? Let me see what you are asking. Okay, can I put it back in one of the rows? Yes, absolutely. You're absolutely right. Okay, but you will see that I will make it pretty much a habit to carry something in front of the determinant, so it's not a big deal. What you're suggesting is perfectly fine. Okay, what you're suggesting is perfectly fine. So what do I have now? I have -12 plus 1 is -11. Then I have negative -6 minus 1 is -7. Negative 3 times -3, that's 9, plus 1, that's 10. And I do the last one, which will give me 0 here. And I have 2 times 4 is 8, plus 1 is 9. 2 times 2 is 4, plus 0, that's 4. And 2 times -3 is -6, plus 2 is -4. Are there any questions so far? Okay, so I'm done with first row, first column. But now I will have a heck of a time, because you see what my entries in the first column right here are. I want to create a pivotal, right? I will have really nasty denominators. There is something out of the ordinary to do here and avoid this. Does anybody see? There's something that is unusual. I wouldn't even suggest that you do it. You have to be, yes, swap columns. Swap the second and the third column and bring this very nice one a place to the left. If you are to do something like this and destroy the pattern that the Gauss elimination method has given you, don't do it. But here you can do it. So I will do it. Allow me to do it. I'm being a little lazy here not to want to work with all those denominators, but can you blame me? Same thing as it is with rows. Everything that we said about rows, as we said before, is true about columns. Why? Because the determinant doesn't change when you replace rows with columns, right? That's the consequence of that really nice property that says the transpose has the same determinant as the original matrix. So I will gain another negative sign, and now I can change them. So it will be positive now. So the two negative signs are going to give me positive. So I will have 2, 1, -7, 4, 4, -5, 11, 9. So you see here, I'm deviating from the regular elimination method, but you can't do it. So now I can eliminate -7 and 4. So this will be 7 times row 2 plus row 3, and -4 times row 2 plus row 4. So back to my elimination path. So I have 1, 2, 4, -3, 0, 1, -5, 7, and now 0, 0. -5 times 7 is -35, ouch, minus 11, that's -46, ouch again. And then 7 times 7 is 49, plus 10, that's 59, big ouch again. And
we forget the minus sign before the matrix.
no, I didn't. No, I didn't. What did I just say a moment ago? Can then somebody remind us? Did I really forget a minus sign in front? I say I did not. Can somebody remind us why not? Exactly. It goes two of them. So minus times minus will be plus. Okay. And then what do I have? I have 20 plus 9, that's 29. And minus 4 times 7, that's -28. Minus 4, that's -32. Okay, this is not good. But here are the great news. I mean, if you have done it like that and you bring it to a 2 by 2, actually all you need to do is compute the 2 by 2. Technically, you need to make it diagonal again. I'm sorry, you need to make it upper triangular. But as you keep going, when you come up, no, it's equal. I never wrote 3. Okay, it's equal. The triple equality, the triple line equality is used in other cases. So the little trick that I'm going to reveal again here, because this can get very ugly, is that once you have it like this, so it's triangular, and then you just have a block of 2 by 2 on the lower right corner, you can actually take the determinant of that and multiply it by whatever entries you have. And you may ask, why can't we do this? And I would like to demonstrate why. So you see, I used as much power of the power of the Gauss elimination as I could. And here, finally, I say, okay, fine, expand with respect to the first row. If you expand with respect, expand with respect to the first column. If you expand with respect to the first column, the only thing that survives is this. 1, -5, 7, 0, -46, 59, 29, 29, -32, right? If I expand with respect to the first column, because all the other things are 0. And now I can expand again with respect to the first column, and this will give me -46, 59, 29, -32. Now I have 46 times 32 minus 59 times 29. Oh boy, how much is this? Okay. 30 times 46, it's, boy, I cannot do this. It's 1200, 1380, 1380 plus 92, it's 1472. Is it? 46 times 32. Oh my gosh, I'm so sorry. I'm an old man. I cannot do these things anymore. Oh, it is 1472, right? Okay, phew. No, it is not triangular. Be careful, it is not triangular, but I was able to apply the expansion with respect to the first column twice. Yes, I stopped here because this last elimination would get the better of me. Hopefully you're not going to have to face this kind of things, but I'm showing you a worst case scenario here. And then you have 59 times 29. So that's 60. Is it? Okay, so I'll take your, and thank you, 1741. So when I subtract the two things, I will get 200 and what is it? 69 minus 269, right? Is that right? And that's pretty much it. Okay. That's it. So here I deviated twice from what you would have done by a usual elimination method. And you can do this because you can work with columns in the case of determinants. I deviated twice. What were my two deviations? Of course, if you write a computer program, you will never need to do that. But my first deviation was right here, where I applied the column operations. Column operations are allowed. They shouldn't spoil the pattern that you have from the elimination method, and here they did not. So they didn't mess up with any pivotal or anything like that. And finally, my last deviation was right here, where I chose not to make it triangular. Normally, you should have made it triangular. That would have taken one brutal elimination. So I chose to expand with respect to the first column, and then I expanded again with respect to the first column, and that gave me 2 by 2 determinant. Okay, and that somehow reduced the operations that I needed. But my general idea, my general philosophy was, let's make it triangular. Let's make it triangular. Okay, and we pretty much used all of the kinds of operations that were needed. Okay, any questions, please?
I have a crazy question. I have a crazy question. Can we split the main matrices to such as 2 by 2s and calculate them?
You know what you're asking is actually not that crazy. It's a very deep question. So, and the answer is it can be done, but you would compute a determinant of matrices, and then you would need to take the determinant of that matrix. So you would need to think of this as matrices and then take a determinant of matrices. It's actually a pretty deep result, and you know, I can't remember if those matrices need to commute with each other. I think there's a condition. I saw such a property. There's something true. I saw it when I was in grad school, and I never used it in my life. But there is a properties which pertains to what you just mentioned, and it's a pretty deep property too. It's not so easy to prove it. I would just say stay away from that. Okay.
Thank you.
Okay, but no, it's not a crazy consideration. There are things like that actually that people have thought about, and yeah. So anyhow, okay. Now, about the any more questions, please? Any more questions? Now, regarding the explicit formula for the inverse of a matrix, here's how it works. So we compute what is known as the, I think it's, oh boy, what's the name? The adjunct of a matrix. Here's the formula. Let me give you the formula and then we'll discuss it. So the inverse of a matrix is the following crazy thing. 1 over the determinant of the matrix. So presumably this has to be non-zero, right? Times the matrix whose ij entry is -1 times I plus j times the determinant of the matrix Aij, actually it's where the Aij matrix is the n minus 1 times n minus 1 matrix that comes up if we delete the ith row and the jth column. And the matrix that you find at the very end, you also need to take its transpose. Okay, that's the explicit formula. And you might think to yourselves, that's crazy, right? Okay, but let's compute it in one very interesting situation. So let's say that A is a square matrix. So you have A, B, C, D, right? What is this matrix now here? So it's going to be a 2 by 2 matrix. So I'm supposed to put as my one entry, -1 to the 1 plus 1, that's -1 squared, so I leave it as it is. But I put what I get if I delete the first row and the first column. What do I get if I delete the first row and the first column? I get just a 1 by 1 entry, which is its own determinant, which is D, right? Then what do I put at the two to place? So second row, second column. If I delete the second row and the second column, then I get the entry A. For the first row, second column, I'm supposed to delete the first row and second column, so that gives me C. But I also need to put a sign -1 to the 1 plus 2, which is -1 to the third. So I need a negative sign. And eventually here I will get a negative B. But here's what you need to take into consideration, that you need to take the transpose of this. So this will be dA negative B negative C. And then you need to divide by the determinant. So that's the explicit formula for the inverse of the matrix A, B, C, D. Here it is. Okay, so sometimes people do remember this formula by heart. Okay. Or you can just reproduce it. I think in the homework, I'm asking you to do this for a 3 by 3 matrix. So let me get you started with this. Okay, I'm going to compute a couple of things for you. So we have what? 2, -1, 1, 1, 0, 3, 1, 1, 1. So you need to start building this matrix, the 3 by 3 matrix. I'm putting it even with parentheses so that I differentiate from that. So how do you build this matrix? So what do you put right here in the 1 by 1, in the 1, 1 entry? You're supposed to delete first row, first column. If you delete first row, first column, then what do you get? You know what? Here's what I can do. I can just put the determinant right there so that you can see it. So what determinant do I get? I get 0, 3, 1, 1. Do I put an extra negative sign? No, because it's 1, 1 place. Then I go to the next one on the same row. So I delete the first row and the second column. And if I delete the first row and the second column, what do I get? I get the determinant 1, 3, 1, 1. But this time I have to put a negative sign, right? Because it's 2 plus 1 is 3. And here you will see that you will have to put them in an alternating way. So now you delete the first row and the third column. And what do you get? You get 1, 0, 1, 1 with a plus in front. Then you go to the second row and first column. If you delete second row and the first column for your, you will get what? You will get second row, first column, you get negative 1, 1, 1, 1. But now you need a negative sign, and you continue like this. Don't forget that in the end, you need to take the transpose of that. Whatever you get is the transpose of that. And you need to divide by the determinant, which you need to compute separately. Okay, so you will have 9. The signs always alternate. So the pattern for this is going to be plus, minus, plus, minus, plus, minus, plus, minus, plus. Okay. So there is going to be a minus here and a minus there. And please understand that those minus signs are on the top of what you find. So if you find the negative number as the determinant, that will become positive, obviously. Okay, when you play with determinants, you always follow this pattern. This pattern is followed when you expand. This pattern is followed when you do the explicit formula. The two things that you shouldn't forget here is, the thing that you shouldn't forget is take the transpose in the end. Take the transpose, and of course to divide by the determinant. Okay? So this is the explicit formula. So this allows us to write, but nobody in their right mind would ever use this for anything more than the 3x3 matrix. That's why, because think about it. If you want to use this formula for the 4x4, can you tell what you need to do? You will need 16 3x3 determinants. You must be very brave to try something like that. So for a 3x3, up to a 3x3 matrix, pretty much you can use any method you like for anything. Any method you like for anything. Starting with a 4x4 matrix, for everything you do, you need to use Gauss elimination, or some slight variant of that, as I did in the example that I gave you. Okay, and that's why I chose a very generic example. I could have chosen a more friendly example and get smaller numbers and use denominators, but I showed you how I try to consider the worst possible case and still get something reasonable. Questions? Last but not least for today, Cramer's rule. Cramer's rule is one of the most beautiful rules in mathematics. You can solve systems with it. Unfortunately, it has two great limitations. What are the limitations for Cramer's rule? First of all, it has to be a square system. Same number of equations are as unknowns. Linear system always. Second, determinant of main matrix has to be 0. It has to be not 0. Determinant, not the augmented, of course, the augmented is not a square matrix, doesn't have a determinant. Determinant of matrix has to be non-zero. If these two things are true, then you're in good shape. Again, you will never use this for a 4x4 system. For a 3x3 system is fine. How does it work? Let me give it to you for a 3x3. Okay, so let me do a1x plus a 2y plus no. Let me use. No, it's better to use different letters here. So let me use b1y c1 z is equal to d1, a2x plus b1 b2y plus c2z is equal to d2, a3x plus b3y plus c3z is equal to d3. So here's your system, a 3x3 system, a generic 3x3 system. I'm going to use to have 4 determinants. First of all, determinant D is the determinant of the matrix of the system. So A1, B1, C1, A2, B2, C2. A3, B3, C3. And here, of course, the assumption is that this is non-zero. We have to assume that. Otherwise, the system is not solved by Cramer's rule, and actually it doesn't have a unique solution. If the determinant is equal to 0, you either have infinitely many solutions or no solution. Then dx is what? You take the column of the constants on the other side, and you replace the column of the coefficients of x. So what does it become? It becomes d1, d2, d3, b1, b2, b3. You leave all other columns as they are. Okay. And it doesn't matter if this is 0 or not. I don't care about that. Then you have d sub y. So d sub y will be a1, a2, a3. And guess what? Same story. So you replace the column of the coefficients of y by d1, d2, d3. And then c1, c2, c3. And finally dz. So you would do that for any dimension, right? For any number of rows or columns. So a1, a2, a3, b1, b2, b3, and instead of the c's, you put what? You put the d's. Okay. So you need to compute these 4 determinants. Not a small task. Okay, certainly not a small task. But it's a no-brainer. With a Gauss elimination, you need to think a little, just a little. Then the solution is dx over d, dy over d, and dz over d. Okay, that's Cramer's rule. That's Cramer's rule. And actually, Cramer's rule is a direct consequence of the explicit formula for the inverse. However, let me do an example in the 2x2 case. So let's say that I have 3x plus 5y is equal to 1, and negative 2x plus 7y is equal to 3. I mean, this is a system that is not so simple to solve by any other method. However, with a Cramer's rule, this is a joke. It's so I have to put on the bottom, I have to put the determinant of the system, and on the top, I'm replacing the first column, the coefficients of x, with 1, 3. These are the numbers on the other side. So what do I find? I find 7 minus 15, that's negative 8 on the top, and the bottom is 21 plus 10, that's 31. Right? And y is equal to, on the top, I will have 3, negative 2, 1, 3. And on the bottom, I will have 3, negative 2, 5, 7. So the bottom, of course, will be the same. It's 31, I know that. And the top will be 9 plus 2, it's 11. I mean, seriously, if you find another way to solve a 2x2 faster than Cramer's rule, please let me know. That's the fastest that you can get for such a generic system. Doesn't get any better than this. Okay, so Cramer's rule is certainly the way to go for a 2x2. Now, even for a 3x3, I think that's a stretch, but yeah, I mean, you can still use it, I guess. Okay. Any questions, please? How did I get negative 8? Let's see, did I make a mistake? So it's 1 times 7 is 7. 3 times 5 is 15. 7 minus 15 is negative 8. Right? I think that's right. Okay, any more questions, please? Okay, for today's attendance, please give me the answer to 3 to the 6th power. Okay, 3 to the 6th power. It has a very nice story, right? Yeah, it's 729. Do you know the story behind this? It's a famous story involving Ramanujan, who he was in the hospital. Ramanujan was a very famous mathematician of the beginning of the 20th century. A very, very unique story. There was a movie that came out recently called The Man Who Knew Infinity. And a mathematician friend of his visited him at the hospital when he was sick. And he said, I came here with the taxi number 1729, but I guess there's nothing remarkable about the number 1729. And Ramanujan said, no, actually, it's the smallest number that can be expressed as a sum of two cubed powers in two different ways, because this is the same thing as 1 to the third plus 12 to the third, and it's also 10 to the third plus 9 to the third. The computation 9 to the third is the same thing as 3 to the sixth that we just computed. So according to Ramanujan, that's the smallest number that has this property. And, you know, of course, the also famous mathematician who was visiting him, Joe Hardy, was once more surprised. Yeah, if you don't know anything about Ramanujan, that's a very interesting fellow to read about. And that will do it for this fine Friday. You really need to do your review for the exam this weekend. Let me repeat what the structure of the exam is going to be. 10 problems. The problems are the same types that you find on the study guide. And I'll tell you right away, if I'm not mistaken, I think the very last problem is from, or the two last problems are from so I'll tell you in a second. I think I did say last time, but let's review it. So if you go to the, so problems 7 and 8 were explained today. 9 and 10 are going to be done next week. So you can review everything up to problem 8. Everything up to problem 8. Okay, so 8/10 of the exam. You will see that actually problems 9 and 10 are just a couple of concepts. The work underlying those problems is just the Gauss elimination method. I mean, if you look at these problems, you will realize that like 7 of them, I think, depend on the Gauss elimination method. Okay, this is why I said, you know, in the very beginning, that the Gauss elimination method is pretty much the essence of this course from a procedural point of view. Okay, then vector spaces and linear maps between them is the other important part of this course. Okay, from the theoretical part. And now I think by this point, we can solve systems, we can compute determinants. So those of you that are taking this course for, you know, that are engineers, have already done pretty much most of the things that you will ever need. There are a few more things. So yes, you will do eigenvalues. We're going to study eigenvalues pretty soon. Okay? Any more questions, please? So I repeat, the exam will be 10 problems long, no notes. But I'm telling you from the beginning what the problems are going to look like, not what they're going to be, but what they will look like. And that's all that I have for you for today. Okay. For the quiz on Monday, great question. I'm going to just give you a determinant, the 4x4 determinant to compute. That is going to be your quiz for Monday. Okay, a 4x4 determinant. Okay. Any more questions? Okay then. So have a great weekend.